Hello and welcome. My name is Peter Bajor, and together with my colleagues Norina Sander and Isabella Németh, we are working on the topic infrastructure and energy management requirements for zero-emission road transport vehicles at future parking lots in Hungary. This aim, the electrification of road transport vehicle fleets, is becoming more and more realistic, and the stakeholders should take care of the necessary investments in road and energy infrastructure as well. The final result we imagine, the ideal system, surely will be smart and bright. The struggle is that how can we get there, especially how to manage the transition process. The electric fuel cell truck, the traditional truck, the electric truck, they seems quite similar, but the way we are using them is strictly different. The way we are charging them, the way we produce the energy they need, requires a new type of thinking, a new approach, both in transportation and in electricity supply as well. For example, you see the electric Volvo truck in the right top corner, which is designed for 300 kilometers driving and 9-10 hours full recharge with slow home smart charging systems, exactly according to the EATR, the truck driver's driving schedule and rules. Possible scenarios, as we were investigating in the literature, the colleagues from Switzerland calculated maximum 5% per year extra power for the electric truck fleet. And they still, even it's a small amount or looking like small amount of extra energy, they still recognize the need for battery swap infrastructure and extensive network development for the home charging possibilities. They were lucky to be able to do this bottom-up investigation. They have all the data about the whereabouts of the trucks in their country because of the special road usage charging system. The Spanish colleagues were not as lucky as they were, so they applied the top-down approach for Spain, and it is a bit shocking that for their country 100% electrification of both personal cars and the road freight vehicle fleet requires half the amount of the yearly Swiss electricity demand, but this 1.5 terawatt hours per day, and the hourly value of required energy is around 90% higher than the peak of the supplied energy today. Naturally, this calculation was based on the average of the average of the averages, but we can still conclude that not only the methodology what matters, but the actual and prospective future conditions of the power grid as well. They are using their systems differently today. This home depot charging versus the battery swap infrastructure, it seems that it's not a choice. We need both of those systems. So as we are coming towards the grid, you can see that charging is easy, and slow charging for 9-10 hours is available everywhere where there is a plug. We should supply that plug on the other side, so it's not just this easy. The battery swap infrastructure, it's questionable because for personal cars it was a catastrophic failure, proven by the case of the bankruptcy of the Better Place company. But the solution exists, and we are using our road freight fleets on a very different way, like our personal cars. The case of Hungary. The strategic energy plan promises maximum 10% of electric vehicles in the whole fleet by 2030, and related to our ongoing nuclear power plant construction, these plants secure the necessary energy input. The nuclear part in our system you can see on the daily profile, this light blue at the bottom. In spite of all these moderate expectations, the infrastructure design is still a question. So in the actual phase of our research, we are trying to match and synchronize the loads you can see at the top right corner, and the supply by the electric network, which is the network you see at the bottom left corner, with consideration of the daily load profile. Here you see our map. We got some data samples from GPS service providers about a 2-week period through the Ministry of Innovation and Technology. This sample contains nearly 5,000 journeys and ended in one of the dedicated 434 identified rest areas. First, we were curious about the pattern of rest and drive period distribution. And we did not find any strong connection like described in the books. You can see how long the driving period was before stop on the horizontal axle, maximum 4.5 hours, and how long the resting period was after at each cases. It can be between 15 minutes and 24 hours. As a conclusion, we can say that according to the sample we analyzed, there should be several other factors like the driving cycle, which affects the decision of the truck drivers related to take their rest periods. Can be congestion, route planning issues, availability of facilities, etc. But at least what we can see that 50 minutes for battery swap and 12 hours for slow charging seems to be available in their time schedule. We just need the infrastructure. Here you can see the daily profile of average rest hours and average driving hours alongside the day. The number of trucks at parking lots follows a similar distribution, these blue dots, as we will see or we saw at the case of the electric load daily profile, which strengthens the need for battery swap refueling. So daytime there are more trucks on the way and or slow charging possibilities are more limited, like at night. You can see here the transport on the left side, the electricity charts on the right side, the network on the top, the distribution in space in the middle, and the distribution in time at the bottom. The distribution of the actual load in space shows similarities naturally because both the transport needs and loads and the electricity needs and loads are provided by the developed economic centers, regions, main cities. The benefit of smart home or depot charging of electric fleets can be identified by the transfer effect, which is the light green part on the chart in the right bottom corner. That is the transfer effect, which means that we can use the existing network for charging when the network load is naturally less at night. The battery swap can be identified by the dark green, so that effect that there are stationary batteries we can charge at a certain time to smooth the load, the increase of the load in the daily electric profile, and both of these can contribute in the infrastructure savings. In the next phase of our research, we intend to identify a limited number of parking lots where the first charging and battery swap systems should be installed and run our calculations or simulations to be able to formulate and evaluate the fitness criteria for sustainable solutions. As a conclusion, the technology exists, the power is coming from the plug if we supply it from the other side. The electric power system in our country today does not provide any storage solutions. As the electric fleet is growing, there will be opportunities for balancing the production and the load, but we need sustainable roadmaps, especially in the transition phase. Thank you for your attention.